Sorting is the process of arranging items in a particular order, typically in ascending or descending order. The items can be numbers, strings, or any other data types that can be compared with each other. Sorting algorithms or methods used to reorder elements of a list or array according to specific rules. So the need for sorting or faster search, where the sorted data allows for more efficient search algorithms like binary search, which can reduce search time from order of n to order of log n. And then data organization. Sorting organizes data in a meaningful order, making it easier to read, analyze, and manage. Sorting also helps in optimization of algorithms. Many algorithms, such as those for merging or binary searching, rely on sorted data to operate efficiently. Sorting is often a prerequisite for optimizing these algorithms. Sorted data helps in detecting anomalies or inconsistencies, such as duplicates or out of range values, ensuring data quality. And now let us look on to the types of sorting. There are many types of sorting such as bubble sort, selection sort, insertion sort, merge sort, and quick sort. In this video, we'll look on to the selection sort in detail. Selection sort divides the list into a sorted and unsorted part. It repeatedly selects the smallest element from the unsorted part and moves it to the end of the sorted part. Selection sort is a simple comparison-based algorithm that sorts an array or list by repeatedly finding the smallest element from the unsorted portion and moving it to the beginning of the list. As we begin our discussion on selection sort, let's start with an unsorted array of numbers. Here we have an array with elements 64, 25, 12, 22, and 11 arranged in no particular order. The goal of sorting is to rearrange these elements into a sequence where they follow a specific order, such as ascending or descending. We'll see how selection sort accomplishes this step by step. Let's start by considering the entire array as unsorted. The first task is to find the smallest element in the unsorted array. Look at each element one by one, comparing them to determine which is the smallest. Once the smallest element is found, swap it with the first element of the array. For example, in the array, the smallest element is 11. Swap 11 with first element 64. The array now looks like 11, 25, 12, 22, and 64. Now, treat the next part of the array, excluding the first sorted element, as the unsorted portion. Again, find the smallest element in this remaining unsorted portion. Swap this smallest element with the first element of this unsorted portion. For example, in the remaining unsorted array, the smallest element is 12. Swap 12 with 25. The array now looks like 11, 12, 25, 22, and 64. Repeat the process for the rest of the array. Each time, find the minimum element in the unsorted portion and swap it with the first unsorted element. Continue this process until the entire array is sorted. For example, in the unsorted array 25, 22, and 64, the smallest element is 22. Swap 22 with 25. The array now looks like 11, 12, 22, 25, and 64. Now, only 25 and 64 remains unsorted, but since they are already in order, the array is fully sorted.
Now, let us look into the pseudocode of selection sort.
Void selection sort defines a method named selection sort that takes an integer array R as input.
It iterates through each element of the array except the last one. The variable I represents the current position in the array. Int minindex equals I initializes minindex to the current position, assuming the element at position I is the smallest in the unsorted portion. Int minindex equals I initializes minindex to the current position, assuming the element at position I is the smallest in the unsorted portion. If minindex is not equal to I, perform a swap. Int temp equals ARR. temporarily stores the value at ARR equals ARR min index, places the minimum element in the current position. ARR min index equals temp, completes the swap by putting the original element from I in the position min index. Time complexity. Selection sort has a time complexity of 2, O, and 2, in all cases, best, average, and worst. This is because the algorithm consistently performs a nested loop to select the minimum element and swap it into place. Best case, 2, O, and 2. Average case, 2, O, and 2. Worst case, 2, O, and 2. Space complexity. Selection sort is an in-place algorithm, meaning it sorts the array by modifying the array itself and does not require additional space for another array or significant extra storage. Thus, its space complexity is 1, O1, indicating constant space usage. The pros are simplicity, in-place sorting, fewer swaps. The cons are time complexity, not stable, unadaptive.